Hello grade 10s, welcome to my video, and if you're new, welcome to the channel. Today we're going to be looking at a grade 10 paper 1 for physical science. Okay, this was taken from the Eastern Cape, written for finals last year, alright, which is 2022 October. So it's a 2-hour paper, and then of course instructions, alright. So they give you how to behave in your paper, the topography and all that. What I am more particular, what I'm more particular about is this one. This is merely an advice, okay? It's merely an advice. If you have good memory and you know enough, you can actually not waste your time looking there. But sometimes when you get stuck, you want to have a look. This one also is important because formulae and substitutions are usually the areas where you get marks, okay? And then the rounding off portion, we are to round off our final. Remember, your final numerical answers. Don't do intermediate ones to already the last ones. So minimum 2 decimal places, but you can have more, no less, but either 2 or more. And then of course give brief explanations. They have to be brief. Motivations, this is my favorite, okay? Otherwise, yeah, that's it guys. You already are familiar with this, so let's look at this one quickly. We're given here that 4 options are provided as possible answers to the following questions. Each question has only one correct answer. Choose the answer and write only the letter A to D next to the question number. Okay, the answer book. Then we're given an example of what that is. 1.11 is E, and that's how we are to answer this question. Okay, not a problem. So let's look into it. Now we're told the physical quantity with both magnitude and direction is called. So when it has both, you know that is what is called a vector quantity, because we are saying physical quantity. So we go in general. So the physical quantity with both magnitude and direction is called a vector quantity, right? Velocity is basically an example of a vector quantity. Is not really a definition, okay? So this is basically an example of a vector. Okay, it does not define a vector. It is defined by that definition. So it's not a scalar quantity. Scalar quantity only has magnitude. Displacement is again an example of a vector. Okay, and we were not asked what is an example, but the physical quantity is a vector quantity. Okay, so the answer is D. So you can see that A and C are not necessarily wrong, but they are not a definition of a vector. Okay, so here we're trying to define what is a vector quantity. Now 1.2 says a girl paddles her canoe against the current in a river. Okay, she's paddling against the current. Great. Now the current flows at 0.6 meters per second downstream, and the girl paddles her canoe at 1.2 meters per second upstream. So basically, if we're to draw some kind of a free body diagram, do you guys do free body diagrams? I don't know, maybe let's just do a vector diagram. So we've got the girl paddling. She's paddling at what? 1.2 meters per second upstream, whereas the stream is doing its thing like that. So this one is going to be 0. 0.6 meters per second downstream. So it says now, which of the following is the resultant velocity? Okay, so we can choose upstream as positive. Here choosing a direction is advisable, so that downstream is negative. So basically the resultant is the addition of these two. So we know that the resultant velocity, okay, we can just say VR is going to be vector 1, which is going to be 1, 2, it's positive, plus vector 2, which is going to be minus 0,6. Okay, so this is 1, 2 minus 0,6. I'm just trying to be a little bit naughty here and do too many calculations, but yeah, you know what to do already. But sometimes it helps to be systematic so that you can understand how things work. Okay, so with that little bit of a calculation, we know that this is positive. So if it is positive, it's going to be upstream as well. Okay, so we're told you 1.8 upstream, no. 1.8 downstream, no. 0,6 meters per second upstream, definitely, because we calculated it, not downstream. Okay, so the answer is C. Okay, moving on. Consider the velocity time graph of an object in motion below. Okay, so we can see there that the velocity is on the vertical axis and time on the horizontal axis. And we can see here there's something, this line right here is kind of saying these are directly proportional. Okay, now which one of the following graphs below represents the acceleration versus time graph? Now what is the gradient between a velocity versus time graph? So we know that the gradient is going to be v over t, right? Right, so, and we can see that this is essentially a constant, isn't it? Because v over t, if you write it in SI units, it's going to be meters per second over second, isn't it? And then this essentially becomes meter divided by second squared. And what is that unit? This unit is acceleration. And as you can see here, the acceleration is constant because it is a straight line. Okay, so if it is constant, when now we're doing an acceleration time graph, it will depend on the direction, but it should be constant. This is not true because it's saying our acceleration is decreasing, and that's not true. And then this one is doing its own thing as well. It's not true, but this one definitely takes the crown because, as you can see, over time the acceleration does not change, which is the rate of change of velocity. So this one is true. D, it's doing its own things. It's saying it's constant, and then we changed direction, but we never changed direction here. We were not told anything. The first graph says we're just moving in one direction. This would have been correct because this is constant and that is constant. The problem is the change of direction with this one, because now we did not necessarily change direction. Okay, so C becomes the answer. Great. 1.4 says, which of the following statements is or are true about an object traveling at constant velocity? We know very well that constant velocity means zero acceleration. Okay, so the acceleration should be zero. Now the question says it travels in a straight line. Well, that's true because we normally deal with what you call equations of motion. We normally talk about motion in, is it 2 dimensions? It's 1 dimension, right? Yes, it's either horizontal or vertical. So it travels in a straight line. That's true. It travels at the same speed as the magnitude of its velocity. Well. The question is same speed. I don't know what are they trying to get to, but if it is traveling on a straight line, we know that the speed and velocity are more or less the same thing. The only difference is that for velocity we need to consider the direction, but for speed we don't really care. So yes, to some extent it's quite correct, but yeah, to say traveling at the same speed, maybe we should say at the same value or the same magnitude. Yeah, doch. Traveling at the speed that is of the same magnitude as its velocity. I don't know. Yeah, but the phrasing of this statement is horrible. Its displacement increases by the same amount in each time interval. Of course, it increases by the same amount. That is true. Okay, in each time interval. And we know that displacement, or should we say distance, when we are doing constant velocity. Remember, speed, or say velocity for example, is defined by displacement, which we can just use S over T. I don't know what you use for displacement, you guys, don't kill me if you don't use S. We used S back in the days, so sometimes, you know, those things come back. And then of course this means our displacement, which is delta S, is going to be V delta T. But with this guy being constant, it means the speed will increase by the same amount, okay? Because the gradient, if you're thinking of a straight line graph without an intercept, this would have been the gradient. This is what is changing. So each time we are changing that speed by just the same value. So that is constant. All right. If it is constant, definitely our distance will increase by the same amount in each time interval, meaning whatever time interval we have, that displacement or speed, distance, does the things that must be done. So we can see that all of the statements are correct. Okay, so yep, 1.4 is D. Now we're told a sphere is released from point A, as shown in the diagram below, passes point B and reaches a maximum height at point B. What? It passes point B and reaches a maximum height at point B. No, man. Can't be serious. I suppose this should be C. Okay. Now ignore the effects of air friction. So this means we are creating what we call a vacuum. How do you write vacuum? Is it like that? Or the so-called closed system? You will hear about this a lot in grade 11 and grade 12. But all it means is that there are no external forces. Everything is the elements that you see portrayed in the diagram. Okay, so now it says which one of the following statements regarding the energy of the system is correct. So the kinetic energy at A is equal to the mechanical energy at A. Ooh, the kinetic energy at A is equal to the mechanical energy at A. Remember, point A is the beginning because sphere is released. If it was released, it means the initial velocity is 0 there, or the speed is 0. Once we are told that it's released, it's the same as when you're dropping something. So it means its speed is not. Now, kinetic energy is related to the velocity. It's half mv squared. So now this means we've got half. We don't care what are those values, but since this is 0, essentially it is 0. But mechanical energy at A is not 0, okay? So this is not correct. Now, the gravitational potential energy is equal to the kinetic energy at B. The answer is no, not true. Because the gravitational potential energy at A, basically is that maximum height, isn't it? So now the problem is that with B is also a height above the ground, okay? So because of that, we know that the only thing that is true is that potential energy, which is EP at A, is basically equal to mechanical energy at B. Mechanical energy is both kinetic and potential energy. So that is the true statement, not A, the potential energy equaling kinetic energy, because that's not the ground level, but it's still a height above. So as a result, it is incorrect. Now the sum of the kinetic energy and gravitational potential energy at B. Now remember, the sum of kinetic energy and gravitational potential energy at B, okay, is equal to the sum of the kinetic energy and gravitational potential energy at C. Yes, in a closed system, that is true, because all it means is that the mechanical energy at B is equal to the mechanical energy at C. And this is true. This is true in a closed system, okay, which we were given a clue about, that we are ignoring the effect of a friction. So this is definitely true. Now the kinetic energy at A is equal to the gravitational potential energy at C. The reality is not kinetic energy, because we saw that it is 0, okay, and the potential energy at C is not 0, okay. So as a result, that is not true. So what is the statement that walks away with the prize? Is that one. Now two sources, A and B, produce a transverse wave, okay? Do you know the difference between a transverse wave and a longitudinal wave? Basically is the pulse, or should we say the disturbance in a transverse wave, it is perpendicular to the direction of the pulse, okay? Meaning if you're dropping a stone into a dam, maybe let's say there's water here. If you're dropping this, as it hits this, the waves will propagate horizontally in that direction and in that direction. But what was the direction of the disturbance? It was perpendicular. But with transverse waves, you could think of a slinky spring. If you pull it in that direction and then you release it back to the position, it will propagate a wave in that direction. So that's what we call a longitudinal wave. So remember those two differences, okay? And then what is the story now? We are told here, source A produces a transverse wave having a frequency of 40 Hertz. If source B produces 1,600 waves in 8 seconds, its frequency will be, okay, now these are type of the questions that you can't just, do otherwise, but you have to do some calculation. So now that we've spoken about this, let's use this space to calculate. Okay, so we know that frequency basically is defined, we know that frequency is defined as the number of waves passing a point or a given point per second. Okay, so now what is the number of waves? It's 1,600 divided by 8 seconds. What is that? So this is 1,600 divided by 8. So this gives us 200 Hertz. Okay, maybe let's not write too much. Okay, now we need to compare this value to the value of that 40. So basically we can just say 200 divided by 40, it's 5. So we know that 200 divided by 40 gives us 5, a ratio of 5. So essentially it is 5 times the frequency of source A. So that is true. So here you can't guess, you have to work it out. Great. Now, the wave in which the particles of the medium vibrate, okay, parallel to the direction of motion of the wave, okay, the wave in which the particles of the medium vibrate parallel to the direction of motion of the wave is produced by, is it an ambulance, an X-ray machine, ripples on the water surface, is it electromagnetic waves? Now, this is very interesting, is it not? It is very interesting. Yeah, this is one of those questions again where you just need to know the practicality of what these are. If for example, you're thinking about the ambulance, let's just think of an ambulance, for example. And then, of course, it has its thing. And people can see that, and it's transporting a patient somewhere. Okay, it's just going on a horizontal road in that direction. So do you see all of these sound waves will be propagated like that, isn't it? So now what happens is this sound is basically producing a longitudinal wave. Longitudinal wave. And then the longitudinal wave essentially produces a situation that would tell us that the medium, the particles of the medium will vibrate parallel to the direction of motion of the wave, because everything is going to be vibrating in that direction, and the direction of the wave is directed that way. So this is quite true, okay, because the compression are going to be ahead of it. The X-ray machine, what can we say about an X-ray machine? Do you guys know anything about it? I don't know. But what I can tell you is with an X-ray machine, if you think of, say, this is whatever produces the X-ray machine, and then you have this person here standing in front here trying to get a chest X-ray done. Okay, let's make this one a woman. Okay, she's standing there, and then this is projecting the X-rays. Remember now, if you're looking at the wave of the X-ray, it's going that way. It's going to hit tissue. That is going to be now pushed, you know, sideways like that. So do you see this one essentially produces what we call transverse waves? Okay. But I don't know if you guys understand what I'm talking about, but all I know is that the angle of action of this X-ray, should we say the X-ray, yeah, this is the wave of the X-ray. As it hits the tissues, they will vibrate transversely. Now that means the angle is perpendicular to the angle of, you know, motion of the wave. This will incite what we call a transverse wave. I don't know what is this one right here. So this would cause what we call a transverse wave, because what we know is that the disturbance is basically perpendicular to the propagation of the wave or the pulse. Okay, great. Easy stuff. So it can't be an X-ray. Ripples on the surface of water. Also, these form what we call transverse waves. Okay, not longitudinal. Longitudinal waves. So basically, this is suggesting that we are dealing with longitudinal waves. Okay, so this makes up what would be transverse waves. Electromagnetic waves, again, electromagnetic waves, we would say they come from the sun, so to speak. If they come from the sun and then they're going through air, you know, the air will move away. This is coming through, and then the waves are going, you know, apart. So again, it gives us transverse waves. So the answer becomes A. Okay. So it's one of those questions that, yep, Yep, if you don't have knowledge. Unfortunately, you can't know everything. So you just have to use the clues. If you're saying longitudinal waves is what you have in the back of your mind, then if this one fits, I mean an ambulance, you can think about it. Maybe X-ray machines and electromagnetic waves may be a bit of a challenge. But again, you guys are given diagrams in your textbooks. So this may be even information in your textbooks. So you should be comfortable with it. Anyway, let's keep moving. Now, two waves, A and B, are produced by vibrating sources with the same frequency. Okay, A and B have wavelengths of 1 meter and 3 meters respectively. Now, if the speed of wave B is V, now the speed of wave A will be, again, it's an indirect question. You can't answer this one without working something out. So let's talk about wave A. Wave A, we know that the speed of that wave is going to be frequency multiplied by wavelength. Right. And then basically they have the same frequency but different wavelengths. So this is F multiplied by, for A it's going to be 1 meters. Okay, which is just basically F. So the V here for A is basically equal to F. Okay, not a problem. But now let's look at wave B. Wave B, we know that the velocity of that wave is going to be frequency multiplied by its wavelength. The frequency is F, but the wavelength is 3 meters. So this is going to be 3F, okay? Okay, so what are we going to do here? We know that they have the same frequency. So basically, frequency is essentially being described by VA. So what can we do now? We know that, okay, this one already says frequency is equal to VA. So we can just sort this one out here and say from here, when we substitute frequency with that, it means VB is going to be 3 into VA. Okay, and then we divide by 3, that cancels out. Therefore, VA is equal to 1 over 3 VB, right? But we were told that for B it's just V, so we can actually take out that. So that is the answer right there. Again, you have to work it out. You can't just guess it. It is not guessable. It is workable. Okay. So yeah, guys, that is the story. So the trick is to know how to solve simultaneously, basically. This is something, I don't know, do you do simultaneous equations already? Grade 10, yes you do. So take your math skills and know that you're going to have to put something into another when there is some commonality between two things. Okay, 1.9 says, a rod acquires a negative charge after it has been rubbed with wool. We did this a lot of times at school. Which one of the following best explains this observation? Positive charges are transferred from the rod to the wool. No. Which one acquired a negative charge is the rod. So the rod means has had electrons added. So that means electrons came from this. Okay, so wool transferred electrons to rod. Okay, that is the story. Ish, bafowethu, come on. Wool transferred electrons to the rod because the rod became negatively charged. Okay, and if the wool transfers electrons, it will remain positive. Okay, so think about that. Just make yourself some simple equations that can help you work through something. So negative charges are transferred from the rod to the wool, not the other way around. So the positive charges, we're not transferring positive charges. Negative charges are transferred from the wall to the rod. The answer is definitely true. Okay, last question, guys. I didn't think I was going to take 30 minutes. Yes, but I did. Okay, consider the circuit diagram with Consider the circuit diagram with 3 resistors given below. Okay. Anyway, all we can see here, this is a parallel connection. Okay, the current splits when it gets to this point into this portion and that portion, and then of course it divides proportionally to the magnitude of each resistor. And then of course conventional current comes from the positive terminal going all around to the negative terminal. All right, and then here of course these currents come together, and then the total current passes through the 3 ohm resistor and it goes back to the battery to complete the circuit. All right, now we're told here, how will the readings on voltmeters V1, V2 and 3 compare with each other? Okay, how do they compare? Well, we know that V1 is, if you see a voltmeter across the terminals of the battery, this tells us we have the total voltage of the external circuit. But of course, you guys only deal with the external circuit in grade 10, even in grade 11. But in grade 12, you will have the so-called internal resistance. But forget about it now. So all that this means in grade 10 syllabus, V1 would be equal to something called an EMF, or the so-called electromotive force. Okay, that is the force that is applied by the battery to move a charge across the circuit, isn't it? Or through the circuit. And then of course, if this is the total, it means these ones are basically portions of it. That voltage and this voltage, they are basically proportions of it. Okay, so what do we need to do? We need to know that V1 is basically equal to the sum of these two. Now let's see. V1 is equal to V2 equal to V3. They are not equal. Okay, V1 is greater than the sum, not greater than the sum, because the sum, actually we know that V1 is equal to V2 plus V3. So it is not greater, but equal to the sum of the two. V2, that one is even ridiculous. V2 cannot be greater than anything that has V1 included. But this one is correct, so that is the answer. Alright guys, so this is how you could work through some of these questions. You can see MCQs can be easy, they can be straightforward, but sometimes you do get hit with some questions that need a bit of a calculation, without which you will not be able to answer correctly. Okay, let's get to the long questions. Now we are told here, a group of people pulling the rope to the opposite directions as shown below. Okay, a woman applies a force of 16 newtons eastwards, and then 2 men apply forces 19 and 21 newtons against the woman. Okay, so define the term resultant vector. So textbook work, you need to be able to know these. Okay, so 2.1, we know that we're trying to define the word resultant vector. Okay, the resultant vector is defined as a single vector that will have the same effect as two or more vectors acting together. All right, so basically a resultant vector, it's a single vector that will have the same effect as two or more vectors acting together. So those are the most important areas to make sure you score your 2 marks there. Okay, 2.2, it says now determine the magnitude and direction of the resultant vector exerted by the man and woman on each other. So here we can just say this is the point of that rope, the center. We saw that the woman applied a force in this direction. That force was 16 newtons. And then the man, one applied a force in this direction. And then another one applied a force in this direction. The other one was a bit longer than the other. Okay, so you can see those vectors are not equal. The other one was 21 newtons, and then the other one was 19 newtons. But pay attention to the fact that these are acting together in the same direction against that. So we can choose to the west as positive because everything is going in that direction. So again, it's always important to think of direction. So we can say now the resultant vector is going to be equal to the sum of these two, 21 plus 19 minus 16. Okay, which is going to be, I don't know guys, is it fair to do it this way? Maybe let's just show that actually it's not necessarily the difference, but it's the addition. But because this is directed differently, we chose to the west as positive, so this becomes let's just do it, 21 plus 19 is 40. Then this is going to be minus 16, right? Which gives us 24 newtons. And if this is positive, it's westwards. Okay, or to the west. Okay, so that is important. How many marks were you scoring there? 4 marks. Okay, so this is important, and that is important, and this is important, and the direction. So that's how you score those 4 marks. Okay, next question. The Banyana soccer team members were busy warming up for their match against Morocco during the AFCON played in Algeria. Okay, not a problem. Below is a diagram that represents the measurements of the soccer field used by 3 players, Dlamini, Biana, and Jane. All right. Anyway, we can see that the length of this field is 100 meters, and from one end to the center is 50 meters. The breadth is 70 meters, and then from the one end to the 18 yards is 60 meters. All right. Okay, not a problem. By the way, I used to be a goalkeeper. I used to be a goalkeeper, you know. That was me when I was at school, guys. You know, this thing is reminding me things now. You know, Anyway, I could also strike out. I could play as a forward, but I was more good as bowling. Bafana. Babona bagola weak laba bazi professionals. They wouldn't touch me. Anyway, I'm being silly, blowing my own horn, but because I was that good anyway. Define the term distance. Okay, distance basically is just the total path. I don't know, man. This is a stupid question. They should never ask this question. I find this question stupid because what is distance? Distance is distance. Come on, guys. That's just a common English word. What else can we say? Damn. Anyway, let's just say it is the total length. Is the total length taken total length taken or traveled. Yeah, let's just say traveled. It's the total length traveled by an object or person. Okay. Yeah. Some questions are really lousy, man. Why would they ask such a question? Really? It's ridiculous. Anyway, it's just the total length. I guess that's what they want. Anyway, Dlamini started at point A. Okay, there's Dlamini right there. What are you doing, Dlamini? Dlamini starts there. Okay, what does she do? She jogged to position E and back to A in 1 minute. Okay, so she did this and she did that again. All right, okay, all right. So if Dlamini does that, it means she moved 100 meters that way and 100 meters back. So remember, we said distance is just the total length, so it's basically going to be 200 meters that she moved. Okay, it says determine the total distance covered. Distance doesn't have direction, it's a scalar quantity. So 3.2.1. We know that the total distance for Dlamini is going to be 100 meters plus 100 meters, which gives us 200 meters. And this one doesn't have direction, so don't think about it. It's a scalar quantity. So 3.2.2, calculate Dlamini's average speed. Okay, in meters per second. So we know that, well, speed for her is going to be the distance traveled over time traveled. Okay, I don't know, guys, do you have formulas about this? Let's just go double check, because at times it's easy to just do what I want to do. So if it is not there, you do it whichever way that suits you. So you can see here there is no formula in this regard, because they know it's the basic thing you can ever think about. So for that reason, we'll just do it our way. As long as there is sense into it, nobody will talk trash. Okay, so the distance was 200 over 1. Yeah, when you want to tell me this girl traveled at this speed, that is crazy. Oh no, 1 minute, I forgot. 1 minute is basically 60 seconds. So time must be in seconds, okay? So, yay. I almost got hit. Took this one too light. So this is divided by 60. Okay, 200 divided by 60 gives us 3. So they said 2 decimal places or more. We're just going to say 33 meters per second. Again, speed is a scalar quantity. There's no need for direction. Okay, great stuff. So what do we do here? Yes, what we do here, you get a mark in physics for writing out some kind of a formula and for substituting into it and for the final answer. And the answer must always have an SI unit. Okay, if it is not there, you are dead. Okay, Jeanne started warming up at point C. So let's see, where is Jeanne? Jeanne is doing things that must be done here. Okay, so what is the story about here? He jogged. Oh, what an interesting. He jogged. Okay, anyway, she is what? She is a he, right? Yeah, she is a he. Yes, people of this country, though. That's something else. Anyway, Jeanne jogged to position E and then ran to position A where she sat down. Okay, Jeanne went this way first to position E, and then she came from position E back to position A where she sat down. Okay, so this means she moved 50 meters that way, and then she moved 100 meters that way. Okay, the distance is 150 meters. Okay, not a problem. We are good. Now we are told to use vector scale diagram to represent the displacement of Jeanne. Show all the relevant information. Use the scale 1 centimeter equals 10 meters. Unfortunately, guys, I don't have a ruler here, so all I can show you is what this is all about. So if we draw a line here, a dividing line, basically, we want a vertical line. We know that Jeanne went that way from here. Okay, maybe let's use a different color for this. Jeanne went that way for 50 meters. Okay, she went that way, so that was 50 meters. So this is going to be exactly 5 centimeters. Okay, so she went that way, and then from the same position she went back double that distance, so to speak. So she went that way 100 meters, which is essentially going to be 10 centimeters. Okay, and then now we want our resultant vector. Our resultant vector is going to be from the starting position to where she ended up, isn't it? It's always head to tail. It's from the beginning to the end. Bloodsuckers must go away. And you can already tell that it's going to be the difference between this and that, which is going to be 50 meters, which is 5 centimeters as well. Okay, so that is it, guys. That is the one. That is the one. So the key thing is that these must be in the same position, and these ones must also be in the same position, and like that. So that is the vector diagram that is needed. I unfortunately do not have a ruler, but if you use a ruler you will definitely have the same thing. But that was a very simple question, but perhaps the skill was that of showing the vectors. Nah. Okay, right. What is the story there? So we're getting a mark for showing this vector, for showing that vector, and for showing our resultant. And then, of course, the fourth mark is for what? For getting the scale right. Okay, maybe the diagram, which includes the scale. That is very simple. Now we are told here, Biana ran from C to D. Okay, where is Biana? So let's take C as on this side. So she ran from C to what? To D, okay? So she ran from C, which is this region right here, and then she went to the 18-yard position. No, this is not 18-yard position. It's just outside, okay? So it's just there. All right. Not a problem. It's not the goalkeeper territory. It's just outside the territory. I went. So she went that way. So what is that? That is that is 50 minus 16, because remember this one is 16. So that is going to be 50 minus 16 meters. Okay, that's the distance she went. And where did she go? And then from C to E, well, what is that? Biana ran from C to D and back to C, okay? Okay, that is something else. C to D and then back to C. And then she went back like so. And then she went the same distance as above, okay? And then where did she go from there? And then from C to E. Yeah, this lady. Yeah, she's doing things. She's doing things. All right, so she takes whatever that is and then adds that. So it's going to be 50 plus those two. That's the total distance she will have moved, okay? Now we're told calculate Biana's average velocity. And then she did it in 1.5 minutes, okay? The average velocity, it's easy. We know that we can just say V is going to be the distance. Should we say distance? Yeah, no, that's where we're going to get caught. That's where we're going to get caught. This one is S over T. Is S over T, okay? Now, displacement is a bit of a situation. You can't take it for granted. Now, let's look at this lady. Where did she start? She started here, okay? This is the start. Now, from the starting position, she went there, back. That means zero displacement, essentially. And then she got displaced until she was here. So now her displacement is basically 50 meters. So all of this flip and flop doesn't matter. So the displacement is from starting position to the end position. So when she went the first time and came back, that means zero displacement. And then the last time she went and never came back, that is the actual displacement. So it's going to be 50 over T. So now this one, there's 60 seconds in 1.5. Now how do we do that? We just multiply that by 60, right? Right, so this is going to be 1,5 into 60. Okay, so we got 50 divided by 1,5 into 60 seconds. So this gives us a 0, comma. Now to 2 decimal places is 56 meters per second. Now the velocity has a direction towards E. Now, so this question can take you down if you're not careful. It can. It looks simple, but it's not. So what is important, guys, is to know how to, okay, first of all, formula. Secondly, this what you call substitution. So you get a mark for the formula, for the substitution, and for the magnitude, but direction, because this is a vector quantity. So you will get caught if you do not essentially include so many empty spaces. Anyway, let's keep moving, guys. A truck mechanic conducts tests after the repair. Now a truck starts from rest at a traffic light. If something is starting from rest, what does that mean? The initial velocity is 0 meters per second, or the initial speed, and accelerates for 4 seconds, okay, in an easterly direction. So here you can tell we're going to need equations of motion, right? A person on the road measures the change in position during equal time intervals. Okay, now the results are obtained in the graph below. Great. So we've got time there, and we've got the displacement. Okay, now we are told here, from this test, write down the independent variable. So we know that whenever we draw a graph where there is time involved, time is on the x-axis. So if we're drawing something like this, we know that time in seconds will always be in the x-axis. So we can say position in meters. So so usually what is on the x-axis is the independent, and then usually on the y-axis it's the dependent. Okay, so the independent variable there is going to be time. In seconds, okay? 4.1.2, the dependent variable is going to be position in meters. All right, but my position looks horrible. Maybe I'm taking a lot of position. I win. So don't be in map. So easy marks, guys. Easy marks. Now use the information in the table above and draw an accurate position time graph, okay, on the graph paper, on the attached answer sheet. So I've already copied it here. So the trick here is to now work out the right scale, because we can see here we've got 0, 10, 20, 30, 40. So we're going in tens on the position. So we can look at this one and say, okay, what can we do then? How many large ones? It's 1, 2, 3, 4, 5, 6, 7. So it won't be enough, eh? It won't be enough. So if we say here, okay, if we say here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, we can say this is 10, 20, 30, 40, 50. How far does it go? It only ends at 40, so we can leave it at that. So now that is the first part, and we can see the small blocks represents 1 meter, 1 meter, 1 meter, papa. And then the time in seconds, it's 1, 2, 3, 4. So it's 1 through 4. So we can say this is also 1, 2, 3, 4. Just to make it nice and big. We don't need to worry about other things. So 0 goes with 0. So there is that. By the way, you need to indicate 0 there. Next one, 1 second went with 10 meters. So there we are. There's power cuts by 4. Sometimes you forget that they do this thing. Where is my phone? Ish, I'm in the dark. I doesn't like to be in the dark. Okay, so now the next one is 2 with 20. It looks like everything is doing this, eh? Yeah, everything is doing what it's doing. So we are fine. So that is easy. Easy. And for grade 10, they're giving you easy stuff, eh? Grade 12s would sweat. They know it. They know it. They will sweat in grade 12. It's no child's play. So there's our graph. It's done and dusted. So basically what matters now is to note what it is called. So this is called a position time graph. Okay? Number 1. So you must have a topic for your graph. And 2, we need to label that this is time in seconds. And then we need to label that this one is position in meters, because if none of these are indicated, you are dead. Okay, otherwise easy marks there. Now calculate the gradient of the graph. So gradient, what you normally are advised to do, pick any 2 points. I can pick these. You can pick any that you want. So here it's quite easy. So you know that this is perpendicular. So it's like a right-angled triangle, isn't it? Yeah. So if I want that gradient, it's going to be change of y over change in x. So we know that gradient is equal to the change in y over change in x. Alright, so always try to write a formula, so to speak. Now we can see that the change in y is going to be 20 minus 10 over, now the change is 2 minus 1. So basically this is just 10, isn't it? Yeah, this is just 10. But remember, this is a ratio, so no measurements. But anyway, this is meters. In fact, it's not cancelling, because remember, this is in meters, this is in seconds. So basically it's meters per second. So you have to write the unit. I almost made a mistake. The units are not the same, so this is going to be meters per second. As you can see, this is velocity, or this is speed. And you can see that this is constant. The gradient is constant, meaning you're doing constant velocity. Okay, because this is what you call position, which is displacement over time. So this is basically velocity. Okay, this is in the forward direction, okay? Because we know that this represents a vector quantity, but I don't know for sure if they will want it. In which direction was this truck accelerating anyway? In an easterly direction, yes. So that should be easterly. It gives us the velocity in the eastern direction. So it's very important. Formula, substitution, answer, and direction, because it represents a vector. Again, it's a hidden vector, so to speak. All right, guys, question 5. A man with a mass of 68 kilograms saw a boy floating under the bridge, which is 50 meters high, okay, above the top of the surface of water, as shown below. He makes a bungee jump from the bridge. Ignore the effects of friction and air resistance. So we are assuming something like a vacuum, or what we call a closed system, or an isolated system. Sometimes you'll hear that word a lot in grade 12. All right, so that is easy. So we can see the diagram right there. There's the man, he's doing his own thing there. There's the boy. So he's trying to save the boy actually, okay? So it's a good thing. Now I told you, calculate the gravitational potential energy of the man just before he jumps from the bridge, okay? 5.1, we know that potential energy is equal to mass times gravitational acceleration times height, okay? Now, let's just double check. What do you have for acceleration in grade 10? We used to use 10, but now they use 9,8, so it is 9,8, so you can't do otherwise. Okay, great. Let's do it quickly, guys. Let's not waste time. This is mass. What is his mass? Is 68 kgs into 9,8 into the height of 50 meters. Okay, so let's do the calculation. It's going to be 68 into 9,8 into 50. This gives us 33,320 joules, okay? Remember, this is energy, so it's measured in joules. So your answer must have an SI unit. So formula, substitution, answer. Standard 3 marks. 5.2, it says state the law of conservation of mechanical energy. Okay, so all I know is that the mechanical, maybe let's write properly. Let's write properly. The mechanical energy in a closed system is constant. Or sometimes you can use the word conserved. Okay? Or remains the same. Plenty of ways of saying the same thing, and it's all allowed. Okay? Easy textbook work, so you should make sure definitions are read and understood. Okay? Don't cram them. Use the law in question 5.2 to calculate the velocity of the man at a height of 20 meters below the bridge. Okay, great. So this means when this man has moved just 20 meters. So here he is now. He's doing his thing there. So he is there. Okay, now we want to know if he has only moved 20 meters, then it means he is how much from the water? He is basically 30. He is 30 meters from the water. So that is what we need to think about. Okay. So let's do this thing. So we know that, well, mechanical energy at the top, okay, is going to be equal to mechanical energy at the bottom. But the bottom is not really the bottom, okay? So this is just the law of conservation of mechanical energy. But at the top, we know that it is just potential energy. So there is no kinetic energy at the top. But just for the sake of being complete, we're going to say mgh plus half mv squared equals mgh plus half mv squared, okay? Which implies now we've got 68 into 9,8 into 50 plus half into 68 into 0, because there's no kinetic energy at the top. So here now we're going to have mass, which is 68 into 9,8. Now the height is going to be 50 minus 20, just to show that calculation instead of just plugging a 30. We don't know where it's coming from. Sorry, plus half into 68 into v squared. That's what we want, okay? Let's clean stuff up. We know that this we calculated above, so it's going to be 33,320 equaling, and let's do this one, 68 into 9,8 into 50 minus 20, which is just 30. So we're getting here 1992 joules. Okay, let's not worry about that. Plus 68 into 0,5 is basically 34v squared. Okay, easy stuff. So this implies that our v squared is going to be that value here, 33,320 minus this 19,992. All of that divide by 34. Okay. Actually, let's not even waste time. But I mean, you know that here you're going to have to take the square root. Okay, maybe let's just show it. Let's just show it, and then now we're going to take the square root. We take the square root, and therefore v is equal to, let's see, square root of 33320 minus 1992. That divide by 34. 34, good 34. This is 19,80 meters per second. Again, they said what? Calculate the velocity. So velocity is a vector quantity. So he is traveling down. You can say downward in words. You can just say down. It is absolutely up to you how you want to phrase that. So that's our answer, guys. So that was a bit of work, ne? Yeah, that was a bit of work. So you can get a mark for the formula. We get a mark for substitutions. We get a mark for the answer and direction, because that is a vector. You cannot ignore it. Okay. Easy. Hey, 5 marks here. When? What is that? Where is the other one? For calculating this height. Yes. Okay. Now, question 6. A transverse wave. Ooh. What is a transverse wave? This is where the disturbance is perpendicular to the direction of the pulse or the motion, right? Okay, of the wave. Now, is generated in a string as shown in a picture below. It took 3 seconds for the wave to be completed. I don't know. What do you mean for the wave to be completed? Because we know, you and I already know that a wave is this movement right here. That's a complete wave, okay? From one point to the next, one phase to the next, like here to there. You can see that that is a full wave. So this statement is again ridiculous, because it says it took 3 seconds for a wave to be completed. Like, ridiculous stuff. A full wave is like that. So this is another wave, by the way. So here, let's just choose another color. So you can see this is another wave. All right, and then we've got another wave there. So I don't know, they should just say it took okay, maybe let's not say it's ridiculous, because maybe I don't understand. You know, sometimes when you don't understand, you just don't understand. Let's not make others look like they are crazy. Okay, so we can see that we've got 3 waves, because this is wave 1, this is wave 2, this is wave 3. So there's 3 full waves, or 3 complete waves. Now it says, for the given wave, write down the period. Okay, so the period is going to be the time it takes to complete a full wave. But we can see there's 3 full waves here. So here, the period, I'm just going to show you the calculation, but you have to just come up with the answer. This calculation you're going to do on the side. So basically, it's going to be the time for all these waves, which is going to be 3 seconds divided by the number of waves. There are 3. So the period to complete one full wave is just 1 second. Okay, so that is the thing. So you're just going to write t is equal to 1 second. So this is what you write. This is just the thought process, because now they didn't ask for it. Okay, but even if you show it, you're not going to get marks. You're getting a mark for the correct answer only. Showing it doesn't give you extra marks. Not showing it is also not going to deduct marks from you. So 6.1.2. It says now the amplitude. So we know that the amplitude is the maximum displacement from rest position. Rest position is this straight line right here to the peak, okay? Or to the trough, whichever you choose. But it is the maximum displacement from rest position to either the peak or trough. You pick what you want, but we can see that from trough to peak it's 1.5 meters. So there's 2 things here, so we need to divide it by 2. So we can say now our amplitude is going to be 1.5 divided by 2, which is going to be 0.75 meters. So again, they said right, so you could show up with the answer. That is your thought process. Showing it or not showing it doesn't add or take away anything, okay? Easy stuff. So let's keep moving. If the wave travels at 2 meters per second for 3 seconds, so this is a different question, calculate the distance d. Actually, we're talking about that, okay? No problem. So remember v, the general wave equation, it says the v speed is equal to frequency multiplied by wavelength. Okay, not a problem. But we can't use this because we don't have the frequency. All right, so that's the problem. We have a problem. But I think we do. We actually do. But let's not use this one. This one is a bit silly. It's not going to help us. We're going to use the general formula for velocity. So we can just say v here is going to be equal to distance over time. Easy stuff. So we know that this implies the v is 2, the distance is what we want, t is 3 seconds. So this is over 1. You cross multiply there. You know that d is going to be 2 into 3, which is just 6 meters. Okay, so distance is a scalar quantity. We're not going to worry about much. So from formula to substitution, basically, and the answer. Now determine the wavelength. Okay, easy stuff. We can see that for 6 meters, We had how many full waves? 1, 2, 3. Okay, so we've got 3 waves for that distance. So this is easy. So the wavelength here, lambda, is going to be the number of, is the distance covered over the number of waves. Yeah, let's not even write too much here. It's just 2 marks, guys. It's not too big a deal. So here we're going to take our 6 and divide it by 3. See, now I'm writing extras. 6 divided by 3, which is just going to be 2 meters. Okay, not a problem. But there's plenty of ways you could do this, but let's just keep it simple. We don't want to stress ourselves, so you're getting a mark for that. And then calculate the frequency of the wave. So now we can use our general wave equation. And we know that this is 2. This is what we want into the wavelength. We got 2. You can say, therefore, our frequency is going to be 2 divided by 2, which is just 1 hertz. Is it 1 hertz or is it 1 hertz? Yeah, doch. It's 1 hertz. Anyway, there is our mark, substitution, answer, with an SI unit. Okay. Question 7. This is a longitudinal wave, right? Using a slinky string. Sorry, a slinky spring. Okay, now the string shown below can be used to demonstrate the wave produced, not produces, but produced by the sound. Okay, great. Now it says identify the components of the wave labeled. And then, of course, we know that these parts are compressions. And then compressions coincides with the peaks of a transverse of a wave. Okay, let's just say we know that those compressions coincide, but even the peaks is just the center, basically the center of the compressions. If you say that is the middle, that middle will effectively be coinciding with the peak of a wave. Okay, and whereas the center of the rarefactions, we call them rarefactions or refactions, or the expansions, or the expansions, basically the center of them coincides with what we call the trough of the wave. Some say a throw, but we will call it a trough of a wave. Okay, and then of course the distance q will effectively mean the wavelength. Okay, technically it's not really directly so, but it would represent a period. But because now we're measuring just distances here, so we can safely say it's the wavelength. So P 7.1.1, we know that P represents compressions. Okay, and the center of which represents the peaks of a wave. 7.1.2, we've got Q. Q represents the wavelength. Okay, the center of which this would represent a throw or a trough, okay, or the dip in the wave. Great, easy stuff. Just need to know these ones from your textbooks. Okay, now 7.2 says the highest frequency that the human ear can hear, right? The highest, that is maximum. Okay, the highest frequency that the human ear can hear is 20, is 20 hertz. All right. Now, a dolphin produces a sound in order to locate prey in water. Okay, great. You can see that it sends a sound when it bounces here and comes back. then it can actually tell whether there is something in this direction to go for. All right? Yeah, these things are very smart, man. If the dolphin produces sound waves of wavelength 5 centimeters, determine by means of calculations whether the frequency produced by a dolphin can be heard by human ear. Yeah, ne? Whoever was writing this one, yeah, when balaka man isingesi siqhela wena tyhini. You want those prepositions, not qhelani. Bhala isingesi siphukile. Sorry guys. Yeah, ne thathu zenza ngcono ingathi ndinguncwana ngelo xesha. Dum. Okay, the speed of sound in water is 1,480 meters per second. This is something you also need to be familiar with, because somewhere, somehow in your grade 12, it is going to be required. Sometimes it may not be given. You need to know it by heart. So there are certain things you have no excuse not knowing, okay? All right, guys, let's keep moving. Hey, I'm taking too much time. Okay, guys, now this is easy. So now all this is trying to say, we need to find the frequency of these waves, because we want to compare it to that which is the maximum a human ear can hear. Okay, so we know that the general wave equation says we have speed equals frequency multiplied by wavelength, which implies the speed here is 1,480 equals frequency. Now the wavelength is in centimeters, but we want it in meters, so this is 5/100. You know, to convert centimeters to meters, you divide by 100. Ne? Therefore, the frequency of the dolphin is going to be 1,480 divided by 5/100. Okay, which is equal to, let us do it, 1,480 divided by 5/100. So I'm getting a 29600 hertz. Okay, which is also the same as when you divide by, you can divide by 1,000 to take it to kilohertz, which is just going to be 29,60 kilohertz. Okay, because they gave it in kilohertz. Okay, let us just be sure. Yes, so kilohertz. Okay, now this is way higher than the maximum, so that means the human ear cannot hear this one with clear quality. It would just be noise. Okay, anyway, so that is the story. So it means the human ear cannot hear that because it is beyond maximum. Therefore, the human cannot hear the sound by the dolphin. Okay, which is, yeah, anyway, not a problem. So we have made a calculation to determine our answer. So yes, we have done it. So 4 marks. So basically formula, substitution, and the answer and the conclusion. That is how the 4 marks are taken. Now 7.3 says a boy standing between 2 buildings, okay, A and B, started to call his sister that is inside building B. Okay, now a sound emitted by the boy strikes the building B and returns back after 1 second. Yeah, doch. Now I'm trying to think about it now. He sends the sound. The sound goes, and then it goes back to him. Now, what are we talking about? What is this time? What is this time here? I want to know. Is this the time it takes for the sound to go and come back? I'm a bit unsure now. The sound emitted by the boy strikes the building B, okay, and returns back after 1 second. Yay! Yeah, doch, this question is doing things to me now. Anyway, now at the same instant, the sound produced by the boy returns back after, okay, and they're talking about this one. I think this question is unclear though. Returns after 1.5 seconds from building A. My problem is this sound of this boy would have gone this way. Quing, 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 quing. Those compressions would go there and hit that building, then come back to the boy. So what are we talking about exactly? Are we talking about this portion only? Or are we including that portion also in this time interval, meaning we sent this away and it took this whole time for it to go and come back? I'm not too sure. Are we saying the same story here, that this is the time of going there and coming back, or we are just focusing on the coming back portion? I'm a bit confused. So it's a bit unclear. Whoever designed this question is not very clear, and this is again another show of poor moderation of papers, because something needs to make sense, guys, unless I'm really too lousy to understand what is going on. But I always make a habit of trying to milk blood if there's no milk, okay? So I don't understand this question. If the speed of sound in air is 340 meters per second, calculate the distance between building A and B. So we know that what is our target is to know how far these buildings are between each other. Okay, so that is the story. So, yeah, I can understand it, but let's do it anyway. So I will do it the way I understand it. Now let's just say from boy to A. What are we doing about it? From boy to A, we know that velocity is basically equal to, we didn't hear anything about the frequency, right? So it's going to be distance over time, okay? Great, which is 340 equals distance over time. We told you this is 0,1, okay? So if we say this is over 1, we cross multiply, we'll know that our D becomes 0,1 into 340, which is equal to 0,1 into 340. I went on 0,1 into 340. So this is 34 meters, okay? Now, let's see, what are we saying basically? We said speed. Speed is a scalar quantity. We didn't say velocity, so I am going to say this is this motion here. The sound had to go and then come back. So for me, I will consider that this is this distance to and back. Okay, it's two things. So this is the one part. And then if we're looking at boy to B, what are we doing about it? So we know that again, the velocity, which means speed, maybe let's write S here even. Okay, now we know that we were told that this is 340 equals distance over time, which is 1,5. What did they say? Seconds, yes. And then this is over 1, cross multiplication would make a conclusion for us that D is equal to 1,5 into 340. Let's just calculate there. So 1,5 into 340. This is 510 meters, okay? But for me, the way I see it, because this is just speed, I would say this is that distance going there and then coming back. So this is basically made up of two components. We can say therefore the distance between A to B is such that we've got, okay, maybe let's just say is equal to, now I would say 34 divided by 2 plus 510 divided by 2. Because to and back is two distances of equal magnitude, is it not? Yes. So 34 divided by 2 plus 510 divided by 2. So this is 272 meters. Okay, so that is the story there. Like I said, the question is not clear, so I'm not happy about it because I'm not too sure what time are we capturing. Are we capturing the time of just the return alone or the time of to and back? So I'm a bit unhappy with this question. So we're going to take it the way that it sounds because it only makes sense that sound went and came back. If it took this time, then it's okay. It is just fine. So that is it. So you can see the 5 marks here. The answer basically is the most important here. So you're getting the answer here, you're getting the answer there, and then the answer here. So we've got 3 marks, and then I would say these steps to know that you have to divide by 2 is mark worthy. So you give it 2 marks there, and then maybe one of the formulas because they are 2, so you can't get for both. So this is how I see those 5 marks. Okay guys, let's move. Question 8 says 2 spheres S and T on insulated stands, okay, carry charges of -7 times 10 to the -9, okay, -7 times 10 to -9 coulombs and 5 times 10 to the exponent -9 coulombs. So basically this is what we call -7 nanocoulomb. This is +5 nanocoulomb. Nano means times 10 to exponent -9. But anyway, you will know these things when you're doing grade 12. You need to know them, please. Alright, so we're told here which sphere S has an excess of electrons. If it has an excess of electrons, it is negatively charged. So it's already going to be sphere S because the charge is negative. Alright, and that means there's extra electrons, right? And if it is positive, it means we're stripped electrons because normally tissues, not tissues, but materials should have a neutral charge. So if it is negative, electrons are in excess. Anyway, so we're going to answer 8.1 and say it is sphere. Yes. Okay. No problem. 8.2. Calculate the number of excess electrons. So we know that number of electrons is equal to the charge over the elementary charge. Okay. On just a single mole of electrons, which is, now the charge is minus 7 times 10 to the minus 9 over minus 1,6 times 10 to the minus 9. You have this constant in your data sheet, so do not panic. Where did it come from? So we have minus 7 times 10 to the exponent minus 9 divided by minus 1,6 times 10 to the exponent minus 9. So here, wait a minute, minus 7 times 10 to the exponent minus 9 divided by minus 1,6 times 10 to the exponent minus 9. Alright, so I'm getting 4,38 electrons. Now tell me, can electrons be can electrons have a comma? Yeah, doch, that's crazy, isn't it? Ish, anyway, let's just leave things the way they are, but I would say approximately just 4 electrons, because I mean, the number of electrons to me has to be round. It can't be a fraction, because we're talking about a mole of an electron here. So yeah, well, whatever you say, guys, doesn't matter. I don't want to mislead you too much, so you can leave it here, you can leave it there, it's up to you. But the formula, substitution, and either one of the answers, you get your 3 marks and you smile. Okay, now we're told here the spheres are now allowed to touch each other and then separated again. Now, in which direction will electrons flow while spheres S and T are in contact? Write down only from S to T or from T to S. Anyway, we know that S has excess of electrons, so it is the one that is going to share those electrons with T. So it's going to be S to T, right? Right. Anyway, so 8.3, we know that it's going to be S to T. 8.4, it says calculate the new charge on each sphere after separation. So we can say now the new charge is going to be Q1. You can just say QS plus QT over 2, because it's going to be an average of what was there. Minus 7 nanometers, sorry, nanocoulombs, no, don't need SI units here, plus 5 nanocoulombs divided by 2. That would be the new charge. So let's do it. So we've got here minus 7 nanocoulombs plus 5 nanocoulombs divided by 2 is minus 1 nanocoulombs. So that means they will each be negatively charged now. Great. That's the one. That's the one. Formula, substitution, answer. Easy stuff. Is there anything more? Nope. That is it. Okay. Last question says now, in the circuit below, the connecting wires and the battery have negligible resistance. Okay. Meaning there is no internal resistance here, and the wires do not offer resistance except those areas that are designated resistors. Now here we are asked a nice question here. Oh, let's just analyze the thing again. We know that conventional current comes from the positive terminal. It's gonna go through that resistor, but when it gets here, it splits into certain proportions according to the resistors. Of course, the higher resistance will take the smaller proportion of the current. The smaller resistor will take the greatest proportion of the resistance. Why? Because charge wants to flow in an area of the least resistance. Okay, and then it goes again here. These come together into one, but of course there is no current when this is broken like that. Okay, but when it is closed, it goes on and completes the circuit. Okay, so we've got a parallel connection in series with the 2 ohm resistor. Okay, now we're told to define the term resistance. What is resistance? So if you guys remember Ohm's law says voltmeter is current multiplied by R. Okay, so you can decide to say you make R the subject of the formula. Is going to be V over I. So how do you define the resistance? Basically, the resistance is, the work done what can we say? Is it the work done? Yeah, the work done to move a current through the circuit. Yeah, it's dangerous, isn't it? Yeah. Is the work done? What is resistance again? It is, okay, let's try. It is defined as the Yeah. How do we define this thing now? How can I go and choke on such a weak thing? Is the voltmeter a unit current? That is crazy, man. But when you are stuck, you run into such survival techniques. You're gonna be like potential difference over current. But no, man, I don't like that. So how do we explain this one? What is the word resistance? Because if we can say resistance, it's a bit of a problem. So I'll just say it is a measure of difficulty which charge experiences how can I explain this thing, guys? It ends on ixesha lento ngoku. We can say it is a measure of the difficulty that charge experiences in passing through a given point in the circuit. Okay, it is a measure of the difficulty that charge experiences in passing through a given point, or should we say a given cross-sectional area. Maybe if we say point is a bit unfair, but maybe say cross-sectional area. it doesn't really matter. Let's just say a given point in the circuit. Okay, that is it. But you can just say it is the ratio of the potential, it is the potential difference over the current, or the ratio of the potential difference and current through a given point in the circuit, okay, or a cross-sectional area. I mean, we're trying to be a bit more, general, rather than to try and force things. Yeah, double check this one, guys. I think I may have fluffed it, but yeah, I got the idea. Anyway, sometimes it's easy to forget things. Anyway, so calculate the equivalent resistance of the resistors connected in parallel. Okay, 9.2.1. So you know that you are told that 1 over R parallel is going to be 1 over R1 plus 1 over R2, and of course going to wherever, but we can see here we've got only these two. This implies that 1 over R parallel is 1 over, what is that, 24 plus 1 over 8. Okay, so if I'm looking at this, I know that 8 is the common denominator, 24. So it's going to be 1 plus 8 goes to 24 3 times. Great stuff. Now, what do? We continue. 1 over R parallel is, this is now 4 over 24, okay? And we can say, therefore, we just flip this. Remember, if this is on the denominator, so it means R parallel over 1 is going to be equal to 24 over 4. So you just flip it. It's allowed to do it like that, or you can just cross multiply and then divide. It's up to you. So sometimes there are some shorthand techniques that assist you in just doing things easily. So 24 divided by 4 is 6 ohms. So do you see the value of the effective resistance is smaller than the smallest of the two? It's always like that. If you ever get anything, it's wrong, okay? Whenever you're doing R parallel, it should be smaller than the smallest of those two resistors. Great. 6 is like this. Is like this. Nah. Yes, I am correct. But there's another technique here that you can use, which also saves you a bit of time. You can just say R parallel is going to be what? The product over sum. So it's going to be R1 times R2 over R1 plus R2. So this is a shorthand technique that you can cram, because it is the essence of all of this calculation. So it saves you a lot of time. R1 was 8 times 24 divided by 8 plus 24. And let's do it. 8 into 24 divided by 8 plus 24 is 6 ohms. So do you see, it's much quicker than this long route. So you can choose what works. But sometimes don't go for shortcuts too much. Learn the technique, learn the longest route, because sometimes it may be your savior. But learn the shorthand techniques as well, because they save you time as well, so that you can pace up. Once a question is easy and you can do either, always choose the shorthand technique. And then if it is, whatever it is, then you go whichever goes first. But don't be too happy doing shorthand methods. They will kill you. Okay, now when the switch is closed, the voltmeter connected across the 2 ohm resistor measures 6 volts. Okay, So now we are told that we have 6 volts here when this is closed. Great, not a problem. It says determine the potential difference across the parallel connection. It's easy. V parallel. Okay, maybe let's do this one first. V1, I don't know, what is it that, yeah, let's just say V1. What are we going to call? Sometimes it's a nightmare. So let's just say V external is going to be equal to V plus V parallel, isn't it? Yes, so now we want V parallel, therefore V parallel is going to be V external minus V. This is 24 we were given, and then V is now 6. So what is that? What is that? That is 24 minus 6, it becomes 18 volts. Okay, so that is it. That is the one. That is the one. That is the one. That is the one. Great stuff. So again, you're only getting a mark here, so they just didn't care about how you came about it, but always know the voltage across the terminals of the battery, we call it a V external, or the external voltage. And this is essentially the total voltage of the circuit. Sometimes you can write V tot, if you like, equals V 2 ohm resistor plus V parallel. There's plenty of ways you can write it, so you can be creative. So you can decide how to show this, but at the end of the day, that is what it is. Okay, let's do the last question now. Now we're told a charge of 18 coulombs flows through the battery in 6 seconds. Calculate the current in the 2 ohm resistor. Anyway, anyhow, we know that Q is equal to IT. Okay, now we're told charge is 18 coulombs. The current is what we want, we don't know it, but time is 6 seconds, which is fine. Therefore, we know that the current is going to be 18 divided by 6, which is 3 amperes. Okay, easy stuff, easy stuff, easy stuff. That would be the current passing through the 2 ohm resistor. But of course, you could have thought of doing it like this and say V is equal to IR. We were told that the voltmeter was 6, the current is what we know, and then this is 2. And then you can divide by 2 there and say I is equal to 6 over 2, which is essentially 3 amperes. So you could do this one by using Ohm's law, and you can use what is being given right now to also, try and use everything there is, because when you get to higher levels, grade 11 and grade 12, you will get questions where you can't really see your Ohm's law coming up nicely. So you need to be able to see things a bit more differently. Okay guys, that is it. I hope you enjoyed the video and you've learned something. I will see you later.